Welcome to the Explainer, developers. Today, I'll be your lead system architect as we boot up the system to hack Cambridge Math 9709. We are focusing specifically on a highly critical module, 2.4 differentiation. We're going to treat every single complex, multi-part math problem you face exactly like a logical algorithm, something you can solve with clean, step-by-step, code-like syntax. Are you ready? Let's dive right into the target mainframe. Before we bypass the examiner firewall, we need to initialize our core modules and load the boot sequence. We've got 6 phases: accessing the mainframe, the method mark algorithm, core differentiation syntax, debugging system errors, beta testing, and finally, our final deployment strategy. Phase 1, accessing the mainframe. Here, we covered the theoretical architecture of derivatives for exponential, logarithmic, and trigonometric functions. To successfully clear the assessment framework and achieve that perfect score, we have to understand the foundational logic of a successful paper. This fundamental architecture relies on 3 key variables: precise definitions, causal relationships, and cross-topic connections. You see, it's not just about memorizing that the derivative of sine is cosine. The principal examiner reports explicitly highlight that candidates who reference cross-topic connections achieve significantly higher marks. For example, if you can link the differentiation of a trigonometric function to finding the stationary point on a curve in a broader coordinate geometry context, boom, that's how you score. Your solutions literally have to act like APIs talking to the other modules in the syllabus.
Moving on to Section 2, the method mark algorithm. This is all about prioritizing process over output.
Let's look at how the grading system actually calculates your score. The Cambridge system relies heavily on the method mark strategy, which acts as your ultimate fail-safe. Systematic processing and showing your work saves your grade, even if your final output entirely fails. Think about it. If you drop a negative sign in the middle of your working, but your core method for applying the chain rule or quotient rule is flawless, the examiner still awards those method marks. You are being evaluated on your analytical depth, not just a superficial final answer. Let's make this super concrete with a little code review. Compare 2 different approaches, DevAlex and DevSam. DevAlex runs all the raw data inputs in their head, skips writing down the steps, and just outputs a final answer. Well, guess what? One tiny arithmetic error causes a massive memory leak, and the system returns 0 marks. It's an absolute fatal crash. Now look at DevSam. Sam documents every single loop of the chain rule logic. Even if a calculation error happens at the very end of the execution, Sam secures maximum method marks for the underlying structure. The takeaway? Be like Sam. Show your clear, structured logic. Which brings us to Section 3. Core differentiation syntax, focusing on our analytical framework. So how do we write clean code and execute systematic processing for complex problem solving? We compile the patch using a very specific standard sequence: deconstruct, solve, evaluate. First, deconstruct. Identify the given information and break the problem into logical variables. Are you dealing with a product of x squared and the natural log of x? Boom, identify the product rule. Second, solve systematically. Apply the relevant principles and execute your analysis with clear line-by-line working. Third, evaluate. Check your results for reasonableness. If you're calculating a gradient and your output is astronomically high for a gentle sloping curve, you should immediately flag an error in your own syntax. Hold up, let's halt the compile screen for just a second. Before we push this final patch to secure maximum marks, you need to optimize your system feed. Subscribe to Ace the Exams at the handle @AceTheExams right now, and turn on all notifications for our weekly system updates. Okay, system optimized? Let's resume. Section 4, debugging system errors. Let's pull up the examiner crash reports. This is a critical system warning issued by examiners year after year. Students lose marks by not showing working. This proves the examiner firewall strictly filters out candidates who hide their analytical depth. If you differentiate e to the power of 3x and just write 3e to the 3x without showing the substitution or chain rule application in a multi-mark question, you're risking a failure. Actually, think of it like the Peel syntax structure used in essays: point, evidence, explain, link, but for math. State your point or rule, provide the evidence from the equation, explain via your step-by-step working, and link it to the final contextual answer. You absolutely have to make your invisible thought process visible on the page. Let's look at the top 3 bugs constantly flagged in the system logs. Number 1, vagueness. Writing "use the formula" instead of explicitly stating "applying the quotient rule because we have a rational function." Number 2, format and presentation failures. Missing brackets, dropping the dx in your notation, or disorganized scrawls that the examiner simply cannot parse. Number 3, dropping the context. If the question asks for the rate of change of a specific physical volume over time, and you just output a raw fraction without units or contextual meaning, well, your solution doesn't match the environment variables of the problem and you lose marks. Moving to Section 5, Beta Testing, it is time for a live interactive code review. I want to run a 60-second mental audit with you right now. Imagine a scenario where a candidate is asked to evaluate a mathematical model using derivatives, let's say modeling population growth with an exponential function. If they fail to evaluate the quality of the evidence, or they fail to identify the limitations of that exponential model over infinite time, where exactly does the failure occur in the system standards? Think about it. Where does the logic fundamentally break? The system crashes at evaluative thinking. Top-scoring performers in this tier must demonstrate evaluative thinking. It's not just about blindly crunching the derivative of e to the x. It's about questioning the assumptions of the model, considering alternative perspectives, and justifying every single mathematical decision with hard evidence. If you just output a number without evaluating what that number means in the real-world parameters of the question, you fail the higher-order assessment objectives, period. Finally, Section 6. Our final deployment strategy, or the cheat sheet architecture. It's time to package our logic and deploy the final string. To truly master this masterclass, you need to internalize the ultimate hack. Connected, conceptual understanding transfers to completely unfamiliar problem contexts. The syllabus is literally designed to throw curveballs at you. They'll present a function you've never seen before, maybe a bizarre hybrid combination of a natural log and a trigonometric identity. But listen, if your fundamental architecture is sound, if you understand the core behavior of differentiation, how to deconstruct, and how to apply the method mark algorithm, you can deploy your logic into any unknown environment and it will run flawlessly. So, as we wrap up this hackathon, ask yourself, is your mental syntax fully debugged? Are you ready to deploy the method mark algorithm and clear the examiner firewall on your next paper? Remember, Cambridge isn't just testing your ability to find a derivative, they are testing your ability to logically structure a defense of your mathematical reasoning. Keep showing your work, keep your syntax clean, and don't forget to hit subscribe to Ace the Exams at Ace the Exams. Click the bell for notifications and leave a comment down below right now with your subject and level. I'll see you in the next explainer.